find the record. So the modality of this class is in person, right? The only way that you see some of your classmates on Zoom, they either had something personal to talk to me, or by university they had to quarantine, and they had approval for participation. So that's why I let them to come in Zoom, just because they can't come out. So if it's snow, rains, winds, and the university then close, we come in here. If I come in here, you come in here. So please don't email Brad or me that, hey, I feel a little bit under the weather, or I don't feel like coming in. Can I not come in and be on Zoom? No, you can't. There are recordings. You can watch the recording afterward. You'll miss the class participation points. That's for whoever is here to get the participation. Don't share the password with those that are not in the classroom. These are your points. So, and think about, based on the whole class, like the whole semester, you can miss 1, 2, maybe 3 of the class participation, and then your final grade would not get too much of a hit. I will drop probably maybe 1 or 2, the lowest of class participation. So if something happens in your life, or you just don't feel like it to come in today, just don't come in, watch the video, lose the class participation. It's fine. Just make sure that you follow up, right? So you don't, like, you're grown up, you don't need my permission. Like, you have 1 or 2, like, okay, I can just not show up. But don't make a habit. It snows, I'm not coming, or I don't know, all the other excuses, okay? It is already making my job very difficult to keep track of who has COVID and is approved by university and cannot come to the classroom, to give them extension and accommodate them. I'm not only teaching 1 class. If it was just 1 class, I would be fine. But I have more than 300 students. Okay, so help me please. And I will help you as much as I can. If I find anybody sharing the passcode with anybody else, all the parties will receive 0, and I'll send them to, what's the committee? Yeah, Coma. I'll send you to them. Well, I won't give you 0. I'll send you to them. They will give you 0. But so don't do that, okay? This is just a way of me also giving you some points, because if you think you can gain a good portion of your final grade just coming to the classroom and do the assignments, right? So this is very easy. I put this system, it has always worked. So help me to keep it going and effective, all right? Okay. Now we had our block diagram reduction that will be graded soon. Homework, Tiff, I saw you submitted the homework. So I'll talk about flow diagram to, Wednesday, and I try to talk about all the rules. So if you have done it before, make sure that you follow what I expect, and then go ahead and you can submit, okay? You can resubmit an assignment. So if you submit and you realize, oh, I made a mistake, you still have time, resubmit. It's all right. So let's see. Today, I'm dividing it to 2 portions. Portion 1, I talk about transfer function. Portion 2, I will talk about, well, we will use MATLAB. So why it's not shared on Zoom? Oh, because Zoom is low down, sorry. So hopefully everyone has a digital device or is sitting next to someone that has a digital device. The idea, I posted the MATLAB, like not lecture, it's like a review of commands on today's module. So if you didn't finish, you can go ahead and check and make sure that you come prepared for next week, because next week we'll use MATLAB. So it's kind of, if you forgot how to use things in MATLAB, this is a good jump start for all of you, but I'll go over them, so don't worry about it. All right, so we talked about transfer function, we talked about block diagram, but more of a block diagram point of view. We didn't look into what each blocks are, right? So today we're gonna do that. I'm gonna use 2 examples, one mechanical, one electrical system, and how do we write transfer function from the equation of motion. You should be very comfortable doing that, because when we develop equation of motion is in time domain, when we use transfer function is in S domain. So we constantly go between them. It's easier to develop in time domain and write the equation, but sometimes it's easier to analyze in S domain. I will show you one example this week. Your book has a table of like most of the circuit and what is their transfer function. So you have access to that, but it's a good idea to be able to do it. So these two examples are going to walk you through how do we do that. I think also this is a review and probably most of you know how to do it. So as we said before, transfer function is the Laplace transform of an LTI system, right? An impulse response to an LTI system, linear time invariant system for a single input and single output. Now, we will set the inertia conditions to 0 when we are dealing with transfer functions, all right? Now, when we go from time domain to S domain, first identify what is your variable, right? Now here if it's x, then x dot x, if we say that the equivalent of is x in S domain is x of s, so x of t becomes x of s, then x dot of t becomes s, x of t, x double dot is s double dot x of s, right? So basically just transforming this differential equation from time domain to S domain. Once we have done that, once we have gone from time domain, everything to S domain, now we can form the transfer function. To do that, you need to know what is your input signal, what is your output. For the same system, you can write different transfer functions, depending on what you assume to be your input or output. So that you have to be able to identify. For mechanical system is a lot easier because it's usually position, velocity. You kind of know what's your output, right? What you're tracking, basically, like position tracking, velocity tracking. For electrical system, it's you have to know what you're looking for. Are you looking for the current? Is the voltage something that you're trying to figure out? So your input output is affected by you. You decide what's the input and output. So once we know that, we identify that our transfer function simply is the output variable or output signal over input variable or input signal, right? We will reorganize our equation that we have. Then we will have our transfer function. From there, we can start our analysis. All right, so let's work on mass spring damper together. All right. Okay, I'll do this one because I'm the mechanical engineer. I'll let you do the next one, which is electrical. But it should be comfortable dealing with mechanical system as well. So I'm going to put my mass here. I'm going to connect a spring and a dash pod or damper, and then this is going to be connected to a wall. I'm going to say that, let's say there's no friction. If I had friction, I have to assume the force from the friction. And let's see, obtain transfer function for the simple mass spring damper. Okay, I draw that. It didn't say that the configuration, it didn't give me any structure. So this is what I laid down. There could be in different orientation. It didn't say anything, so I'm using just simple mass on the flat place. With an input force of RT, okay, I have an information. There is an input force of RT, so I'm just gonna say this way. Do I know it? No. I'm assuming there is a force that could pull this object or push. I'm just gonna say pull, all right? In this example, the output variable is the position of the mass. Okay, good. So I kind of know what my output variable is. So if I measure the position of mass from here, you can put that anywhere, right? But you have to show your assumption. So all of these are your assumption. I'm going to say, if I move this way, if this cart move this way, this is going to be x of t. So this is your output variable, right? So I made 3 assumptions. I didn't have the orientation of this. That's what I assume it is. I wasn't given. There was a force, input force. I didn't know the direction of that. I chose one direction. I assumed it going to be to the left. Then the position of the mass was the input. Again, I didn't know which way is the positive direction. I assumed the positive direction. Just to make my life easy, you see that my R and my X are in the same direction. Just makes it simpler. You could point both of them to the other side, right? So try to, when you're solving an example, try to write down your assumption and make it as easy as possible for your future calculations. So now here, well, now I have to find the transfer function. So where do I start? Okay, cool. I have all the assumption. It looks pretty. Now where do I start? What's that? Did someone say something? Please say.
Take a block diagram.
Okay, so let's brainstorm how to solve before we start. I'm going to put my pen down. That's usually what I do before actually writing something. Think about it. So block diagram, and what do we get from the block diagram? Because someone asked me, how would you solve a problem you've never seen before? I'm showing you my train of thought. How would I usually approach? So that could be your approach if you like it. So I need to write a transfer function. What is a transfer function? Let's work backward. Yes. So transfer function is the output over input, right? So I know I need to know what are the output and input. So that's a good start. Like, again, we are building up. So these two are, you're going to see two simple examples. The idea is to find that process of solving this. So I know transfer function is output input, right? Now, output variable, input variable. Can we identify that? So my output is my x position, right? And input is R of t, but transfer function, what does this quickly tells me? Transfer function. What does this imply? You all either know it or you know it and you're lazy, huh? Yeah, there's a relation. We have to state everything in S domain, right? So I know, even though my output is x of t, I know I need things in S domain. Right? So now my transfer function, if that's my input and my output, see, I haven't solved anything. I'm just writing down my process, thought process. Now, if I call the transfer function t of s, what am I looking for? Output over input. So my output variable is x of s, r of s. So I know this is what I'm looking for, right? R of s, you have it, like it's just your input, it's just one thing. You don't know what it is, could be sine, cosine, could be just impulse function, whatever you'll be given. We need to find what x of s is, right? How do I do that? So there is a relationship, like you mentioned, there's a relationship. So how do I find that relationship?
Isn't it based on the spring?
That's one of them, yes. What else? Okay, okay, so we need to know what k is. Let's say we call it k. The damping constant is b. I also know the mass is m. So I know all the pieces, like all the components, right? How do I connect them? Like, how do I say how they're related? Okay, so we need to find the forces, right? So I'm going to write down the forces. So let's say force from spring. Okay. Do we know the equation for that? Kx. Yeah, I didn't expect you to know, but thank you. Kx of t. Yeah, it's been a while, I know. That's why I chose this example. Okay, then the other force is from damper, right? Which basically is a damping force, is damping. What damping is doing? What does damping do? How many of you have a motorcycle or a bike that has damping in it? Or car? Most of you are at least like you like rode a bicycle. What does damping do in your bicycle or motorcycle? Some part of it is vibration, but what does that vibration do to? Like, why does that create? Okay, damping, good. Part of it is vibration, and vibration becomes because so if something has velocity, then you can have that. You can have first of all advance, and then you can have vibration, right? So the equation for vibration is complicated. But damping opposes velocity. Spring opposes change of displacement, right? So that's why K is a coefficient, right? A coefficient times displacement. So if I want to resist with displacement, I can say this displacement equal Kx, this force will oppose this. All right, so if you have that spring, if you calculate the force, you will say there will be Kx force applied on this. So if you pick a very large K, your resistance to change of displacement will improve, right? You have a great resistance, you can't pull it. For damping, it would be Bx dot because it is opposing the velocity. So now why I'm explaining all of this to you, the reason is we memorize this equation, then we forget after 2-3 semesters. It's been a while, last time from your physics. But if you learn how these forces are created or why do we write them the way we do, you never forget. So spring opposes displacement, damping opposes the velocity. It wants to slow you down. So if someone wants to slow you down, it's against your velocity, right? So that's the damping force. So we figured out two of our forces. We have an external force of R. Now, if the object has a mass of m and you give it a velocity, do you think there will be another force involved?
Could be
mx double dot is the inertia, right? So if you start moving, I have to oppose force to stop you, right? Because you have inertia. Even if you're not changing your velocity, or so I have to sit here. Or if you're not even changing your velocity, I still have to apply a force to hold you because of that inertia. So the third thing here is the inertia. So for every mass spring system, we always will have this if the component is available, right? So some system, they don't have damper, they just have a spring and mass. So that Bx dot is not available. Now I know there will be an Mx double dot, which is due to the inertia. Now, how do I combine all of this? Why do we want to combine? Like, what is this thing we want to come up with? Yeah, but what is it? What is this called? Like, you're modeling our system or coming up with equation of motion or dynamic equation. So that's the thing that you need to always find. No matter what system you're given, you have to find the equation of motion or dynamic equation, right? Now for mechanical system, it's literally motion, like something will move. Electrical system or networks, you have current moving in, or there's a signal depending on what your system is. Right? So depending on your system, you have to find the equation of motion or dynamic equation of that. So now we kind of work backwards to get here. Now, usually I would start from, all right, sigma F is MA. You remember this, right? So A here is X double dot, right? So I'm going to write Mx double dot of T. So I have Mx double dot of T, and rest of it is the addition of all the forces. Now, we have three forces, right? The input, force from the spring, and force from the damper. Now, there is one little thing that we need to pay attention to. I remember the assumption that I said the direction of the applied force from the R of T is in the direction of my displacement. If you were to show me the direction of force applied from the spring to this system, which way would it be? So I'm trying to pull it to the left. Where do you think the spring force would point to? To the right, to opposite, right? How about the damper? Opposite, because damper and spring are trying to resist this motion, right? That's the model of the system. So when I write the sigma F, let me put it here so I can put everything in order. So this sigma F would be RT positive because the direction of my displacement is in the same direction, minus negative Bx dot of T, negative K of X, because if I were to show the free body diagram, This another term you might have heard before. And mx double dot sits here. Is the inertia, right? It is there because things are moving. That's all. All right. Now this becomes mx double dot of x double dot t, sorry. So if I rearrange this now, I'll get mx double dot of t plus bx dot of t plus kx, oh, kx of t, I kind of wrote that. X of t, yeah. If you point that out, you were right. It should be like this. The r of t. Now this is equation of motion in time domain. Cool. I even know what my input is, r of t. What's my output variable? What am I trying to figure out? X of t, the position, right? So this is a second order differential equation, right? That's why I have x dot and x double dot. So I exactly know what's going on. I know I have second order differential equation. I have an input. Now I need to move everything to S domain. Now you should be able to do that because you have that equation. This is what was missing. Now, if I convert to S domain, I can get m s squared x of s plus b s x of s plus k x of s equal to r of s. How do I know that? From right here. So that's why I needed to know what's the equivalent of S domain for differential equation. Now, if you look back so every time it's really good to look back, see what we were trying to figure out. We were trying to find x of s over r. So now if I factor this out, okay, or s, then x of s over r of s becomes 1 over ms squared plus bs plus k. That's the transfer function. We will model a lot of systems like a mass spring system. So if you are interested in robotic, if you have been in my robotic class, you remember that we use this system to develop the controller because that's all that happens. We can model everything in physical world as a mass spring system. It could be systems of mass spring, but you can always model because velocity and damper, position and spring, and your acceleration and the inertia, right? Now, we will see this a lot. Now I want you to solve this one, an RLC circuit, put them all in series. I'll draw that. I want you to obtain the transfer function, right? Hopefully you remember the equations, but I want you to still think about it a little bit. So this is positive, negative, that's V of t, R, L, C, and what's the input, what's the output variable? Try to figure out if you can define that, and then write the transfer function. I'm gonna give you a little bit of time just to get started, and then I'll solve this. I'll just walk around. So if you forgot, 2020 is a good time to review, because we're gonna use a lot of that. What? I don't know. You need to tell. You need to figure out. Yeah, I need to. I want to see what's your engineering nutrition. I really, when I teach or when I solve problems, I want to know how it is used for my life. If it's not, I usually don't care about it. These are useful. So try to understand that. It's okay. Try your best. And then Jeffrey, what's the input here? The voltage, that's what you're supplying, right? So voltage will be our input. So VFT is my input variable. Oh. David, do you know what the output would be?
Voltage across the capacitor.
So if voltage is the input, then it's the input. Voltage across the price is still an input. You're just close. Current. That's the output, right? It's just when you have voltage across that, that's your input. What you're trying to find. So the current is going to be your output. Now, if you do the thing I did, what is the transfer function you're trying to find? T of S, H of S, whatever you want to call it. So output I of S over V of S. Now, the thing is, in electronics, you could say, you know what? There was no voltage. I wanted to charge this out of the capacitor. I want to charge the battery so that the current becomes your input, the voltage becomes your output. Really depends on your problem. Here, there's different things. Now, what's the next thing we need to do to find that? Okay, so let's say we have RL and so we know what the variables are. So what is the next step? Okay, so what is this thing that you're trying to do? You're trying to find the equation of this, right? The modeling. You've done KVL. That's basically you're trying to do KVL, you're doing separately. So you can write a KVL, right? To find voltage drop across all of these elements. The voltage drop across capacitor, inductor, resistor should be equal to your voltage source, right? That's a good start to write that equation. You need an equation to connect these things together. So we always, from time domain, once we know what our input and output is, we need an equation. Now, there are different ways of writing equation. I'm going to use KVL, right? So I'm going to say that, okay, V of T, the voltage support that provided, it should be equal to, I'm going to say VR of T, drop across resistor plus VL of T plus VC of T. Now, you could also say, oh, this is positive, negative, positive, negative, positive, negative. This goes negative VT, positive VT, negative, negative. You could do all of that too. Same. We'll give you the same result. Now, if I write to this is ITR, right? Plus, now you need to know the equation for this. Like, hopefully everyone still remembers 2020. If not, good chance to review. We basically always use basic equations. Like if you know Ohm's law, you're probably good to go. All right, so this is time domain, right? I created V of T and created I of T. So if I factor IT out, I kind of have both of them, right? But I need to transfer this to S domain. Do you remember what are the equivalent of those in S domain? Right. From here is easy. Yes, I'm going to factor out all of them. Right, so we got transfer function for this. So if you look at this, does this resemble something you saw before? Like a slide, that's a slide. Both of them are second order differential equation, and you see that we will discuss, it's actually very beautiful how they're connected. You have s squared s and 1 over c. We will see next week that our mass and our inductor are actually doing the same thing in the system. So if you have them, you can just directly go here. So you can kind of anticipate and write the equation of motion without actually going through all of that. Because if you know the equivalent of the mechanical system and you know that equation, you can just write it. The electrical and mechanical system are equivalent. You just need to know which part, which component is equal to what component. But both of them, we have the transfer function. Now, I'm going to show you this really quickly. Here, I gave you an appendix for all the transfer functions because you could have amplifier, right? You could have, I don't know, like differentiator in your system, any filters. You have all the transfer functions already written for you. So if you saw any of those, you can just directly use those transfer function. But you should be able to write the equation and go from time domain to S domain. Most of you have done this before, right? In circuit, I'm sure that in 2020 we've done this. All right. Okay, so now we found the transfer function. Two simple example now. So what? What do we use them for? We use the transfer function to analyze the stability of our system, first of all. Now, how do we get the information for the stability? When you look at transfer function, you have a numerator and denominator, right? If you find the roots of the equation of the numerator, you get the zeros. If you find the roots of the denominator, you get the poles. Now, the poles are the ones that we are interested in, but we don't want to ignore zeros. But for now, we will focus on poles because they have the most effect on our system, but zeros will be sometimes, will have a part as well. Now, what are the poles of this given transfer? What are the zeros of this given transfer function? What is the zero? Negative 12. So you get the numerator equal to 0 becomes that. Now the poles, how many poles this have? 4. So 0, negative 4. And if you solve that, I wrote it somewhere, plus minus 39 divided by 2, which is negative 5.5 plus minus 3.21 J. So this has the imaginary part. Now we're going to show them. Do you remember the S-plane we talked about? So imaginary real. So we are looking at the 2D. Remember this, if we make this a 3D, we have the frequency on the other slice. So we are only looking at the real part, imaginary part. So we could show our pole and zeros. So we will show zeros with a circle. So this is negative 12. And then the poles with a cross mark. So there is a pole at 0, it's called origin. There's a pole at negative 4. Then you have a pair. One is here, one is here. So this is 3.2 J, negative 3.2. And this is negative 0.5. Now, again, I know you all know this, but we are going to use this simple information every single time we are analyzing. So when I ask you to analyze if this system is stable or not, you have to do everything we have just done until here. Then from here, we start our conversation or analysis. All right, you should be able to do that comfortably for any system. Now, is this clear? Any questions so far? No? So there is a specific characteristic of a system that happens based on where the poles and zeros are. If poles are on your left-hand side, your system is stable. If it's on the right-hand side, your system is not stable. You could also have poles on your imaginary axes and also on your origin. Every one of these means something. So today I'm going to explain these two and also two theory. We will use those constantly to analyze our system. All right. So before I jump into the stability part, let's cover the two theorem. One is called initial value theorem. Have you heard of that? IVT. What is IVT? What is initial value theorem? What does it tell us? It's okay. You can just like whatever you remember. Initial value, right? So when we talk about initial value, we are usually talking about time domain, right? So what's the value of this function at time 0 or at time start? That's initial value. Now, the initial value theorem is in S domain. So when you have the transfer function and it's in S domain, there is a way of finding out the initial value in time domain. That's why this theory is important. You don't need to know the equation of the differential equation in time to find out the initial value. It tells us that if we have the transfer function, we can write the limit of, we can get the limit of S times our transfer function. And if you send S to infinity, whatever value you get is the initial value in time domain. But we are using the S domain, right? So let's work on that example. Let's see if you can get the initial value. Write that equation and tell me what the initial value is. One. So you can say you multiply that and then factor the highest degree. So this tells us R at time 0 is 1, time domain. So pay attention to this two domain change, right? This one part, if you forgot, that's where math comes in. So the language of engineering is mathematics. So that would be R0 is equal to 1. Now we have similar theorem for final value. So we can find the final value of a function or a model of a system if we have their transfer function, right, in time domain. Now, why is this a good thing? Final value is also called a steady state. So it can help you to predict where the system will end up as time goes to infinity, right? The time goes to infinity means S goes to 0. So similar limit of SFS, this time S goes to 0, which is like time goes to infinity. Now, there is a caveat, there's a catch here. You cannot use this for every system. This only holds only if all poles are in left-hand side or at the origin. So this is only for a stable system because steady state is meaningful for a stable system. If you have on a stable system, there is no steady state, there's no final value. The system is going to berserk. We don't have anything berserk in engineering, right? So what is the final value for this function? First, you have to look if applies to this. Then tell me what it is. So R infinity, limit of what's this? This should be easier. 0, yes. So this means R infinity is 0. So the steady state, so in time domain. So information we got from S domain regarding the time domain, the final value of a system. Think about, you have a mass connected to a spring, dampered, but it is pointing downward to the, like, dangled down like this, and you pull. That's a system, right? If I pull and let it go, what do you expect after time goes to infinity? To this mass, what do you expect to happen? What do you expect to happen?
Go back to 0.
Where it started. It could, like, we don't know if it was 0, back to its position. So you know there will be a final value for it, right? The final position. Now, instead of having the system, if I had a transfer function, but I didn't know what the system is, right? I couldn't assume what the system is. And then it was a stable system, so it would get somewhere. I could use that transfer function to find the final value, where it will end up. And that is in time domain. So you could use that model to find where is the start and then end up without even bothering to look to convert everything and solve in time domain. Solving a system in time domain means solving that differential equation. Without doing that, we gave two very important information. All right. Now, if we find all the poles and all the poles are on the left-hand side, it tells us the system is also stable. So it will eventually would reach a steady state like position, right? These are really very important when we're designing a controller. All right. Now, so I think this is the last slide. Yeah. So after this, you will work on transfer function. I will extend that because you will not have time, but I will give you the password for today. So graphically speaking, this is also really important. Imaginary and real. So this is your right-hand side, right-hand plane, left-hand plane, origin, and this is your imaginary. So if I give you this transfer function, T of S equal to 1 over S minus 1. Can you tell me what is the final value for this system?
The pole would be on the right.
So the first thing is you find the pole at S equal to 1. So I have solved, I actually wrote the limit. So you can actually wrote the limit. I'm doing it for 1 limit S 1 over S minus 1. S goes to 0. So actually, if you do that, it will tell you it's 0. But this is wrong because we can't use it. If you draw this, the response actually is something like this. It goes to infinity. This is not a stable system. So I could use the final value theorem, but it gave me a wrong answer because I can't apply it, right? How about TS equal to 1 over S plus 2? Can I use final value theorem to find the final value for this? Yes, because pole at S equal to -2, which is here, left-hand plane, right? The other one was S equal to 1. This is 1. So that's right-hand plane. How about TS 1 over S? Can I use final value theorem to find the final value for this? Pole at 0. Origin still is acceptable. So now all you have to do after is limit S, transfer function, S goes to 0, you will find it. And then how about 1 over S squared plus 4? No? Yes, no, why? So S plus minus 2 is on the imaginary, not acceptable, right? But if it was something that was, for example, become here, it's fine. It's on the left-hand side. It just has imaginary component. So having imaginary component does not mean you cannot apply. Being on the imaginary line, it means you can. Yes.
Why is the plus minus on the imaginary line?
J, because I forgot the J.
Oh.
Yeah. All right. So if you look at the response of system like this is always, so whenever you are when the pole is only on imaginary, your response always looks like this. Always. Like the equation might be different, but if the pole is on imaginary, you always have this response. So you see that this system is unstable, but is bounded. It always bounces between 2 points. It never reaches to any point, but we call them bounded instability. There are some systems that like you go like really crazy. Those are unbounded and unstable, right? So this is still, we cannot use that for FVT. All right. What I'm gonna do is I'm gonna give you the password for the class participation. I'm gonna extend it to tonight. It's just 3 questions, but since we ran out of time in class, so you can do it tonight. I want to look at the MATLAB part, okay, for the remainder of the class. You have a few minutes, right? Yeah, okay. Let's do that. I'm gonna stop the recording, but I'm not gonna go out of Zoom. Continue recording. Going to MATLAB online. So if you have iPad computer, go to MATLAB online. Hopefully our internet will cooperate and we can, yeah. And the lecture that I'm like the material that I'm following is very simple. It's on today's module. It just said MATLAB review, something like that. I can't find it from from here. Yeah, MATLAB transfer function. Okay. All right. So very simple stuff. You can follow that and do all of those on your own, or you can follow me. Either one works. So at the beginning, so I wrote a few things. Just a review, you can build a polynomial. Let's say PS equal to S squared plus 3S squared, 3S, sorry, here, not squared, plus 4. So you can create a, this was for 3, that's why, yes, squared. All right, so here, the coefficient of S to the power 3 is 1, so that's 1. Then the next is 2, the coefficient is 3. We are missing S in this polynomial, so the coefficient is 0, and then S to the power of 0 is 4. So 1, 3, 0, 4. If you run this, I'm going to run section, and then you get, so we're creating, let me get this up here. All right. We are creating that, so I created P, a vector that has all of those values. Now, if I want to find the root of that polynomial, I can say root of P. So it knows P is the coefficient of my polynomial, right? So you can use that. Now, let's say you have P, you want to write down, you want to find out what is the, so you found the root. Now you want to find if these are the root of a polynomial, what the polynomial could be. So you can see P is poly of R. So finding polynomial from the roots, you can use this command. It's useful. Why? Because we usually, when we are defining transfer function, we have a polynomial on the numerator, 1 on the denominator, right? And sometimes we just, you might just know poles. If I wanted the pole of system to be like that, what would be the polynomial to represent that? Then you can use this command to give you that polynomial. All right. If you needed to multiply some polynomial, like the example we had, you can use com, and then you create, for example, polynomial q, p, and then if you use com, it will multiply them together. You see that a lot of times to find the pole and zero, you need to have a polynomial to find the roots, right? So use com first, then find the root of that. So these are all kind of review if you forgot how to do it. If you have a polynomial, for example, in S domain, you want to know what's the value for a specific pole of the function, you can use polyval. So here, polyval at S equal to -5, what does it mean? The pole, let's say the pole of that system is a -5. I want to know what's the value of that denominator. So you can simply use this instead of using your calculator by hand. You can use polyval. So pretty simple expressions for like the start of using MATLAB for control. Now, the next thing is I want you to build a transfer function. So if you have the lecture slides, I gave you a very simple transfer function. It has numerator, denominator, and you can use MATLAB to reduce a block diagram to the final transfer function. All right. So I'm going to pull up this. So this was what I just went over. Now you can use TF to create transfer function. Now to do that, you need to have a numerator. So you have a polynomial for your numerator, a polynomial for your denominator. So when we have two vectors, that's why you need two vectors. Then you can create a system, call it whatever you want. TF parentheses numerator, denominator. So create G1 and G2. Now, if they are in series, you can either add them like system1 plus system2, or you can use the command series to add those two together. You also have a command for parallel. So you see that if you had a block diagram you needed to reduce, you can see the process and code the process, and it will give you the final solution. So for your homework that you're doing by hand, if you wanted to verify your final solution is correct, you can have this code and you can even submit it to show me that you evaluated it. This part is optional, but it's good for you to know if your solution is correct or not. So we have series, parallel. Then the next thing, if you remember, we had feedback, right? So if you have a feedback loop that you want to reduce, you will write feedback, your system, and you use 1. Now this is for negative feedback, okay? Now, we will work on this example later. I just wanted to show you the main command here is TF that you might not have seen before, and parallel, series, and feedback control. You can go ahead and solve this example, or we will solve, there are 2 more examples. We will solve these 2 multi-loop reductions later. But I want you to at least go over until PZ map on your own. These are just the commands, nothing difficult for you. All right. Hopefully nothing difficult. All right, that's the end of today. Come prepared on Wednesday. We will do flow graph diagram. And if there was time, we will continue the MATLAB. I will always use MATLAB at the end of the class to just remind you all the commands.